So, we will take another example now on the coke consumption related to blast furnace. So, that is a 2 million metric ton per annum iron blast furnace is operated at a coke rate of 500 kg per ton of hot metal. Assuming that 1 ton of coke produces nearly 4000 meter cube of blast furnace gas, and every cubic meter of the latter on an average contains 20 gram of dust. So, estimate the amount of equivalent coke in the top gas and dust produced on a daily basis. So, one can assume 1 kg of coke is equivalent to 32,000 kilojoule of heat, and the typical calorific value of the blast furnace gas is about 3600 kilojoule per meter cube. So, on the basis of these data, we can easily calculate the daily production of pig iron 2 million metric ton per annum. So, 2 into 10 to the power 6 tons it comes, and because it is per annum. So, basis on per day 365, it will come 5479 ton per day. So, the amount of coke consumed per day is about 500 kg, which is about 0.5 ton into the daily production of pig iron, which will come at about 2740 tons per day. So, and now we know it is given that 1 ton of coke produces about 4000 meter cube of blast furnace gas. So, 2740 ton will give you about 11 into 10 to the power 6 meter cube blast furnace gas. And also it is given that 1 meter cube blast furnace gas has a calorific value of 3600 kilojoule. So, total calorific value of this blast furnace gas, if we say on the per day basis, would be quite high. So, 3600 into this. Now, 1 kg of coke is equivalent to 32,000 kilojoule of heat. So, 1 ton of coke is equivalent to 1 ton of coke would be equivalent to 32 into 10 to the power 6 kilojoule. So, this is kg. So, 1 ton is about 10 to the power 3 kg. So, which will give you 32 into 10 to the power 6 kilojoule of heat. So, on daily basis the total calorific value of the blast furnace gas can be estimated. So, it would be 3600 into 11 into 10 to the power 6, which that gas which we are getting it divided by this equivalent heat. So, it gives you about 1237 tons of coke. So, this sort of coke is required per day for the blast furnace. So, if you assume that and if we assume the current price of coke is about $250 per ton, the cost of it would be 250 into 1237, and if we convert our dollar into rupees, so exchange rate if we take 60, so it comes almost 19 million Indian rupees or about 0.3 million US dollar. So, that is a huge amount. So, a small saving in this can result a big saving in the price, and that is how people are trying to decrease the coke consumption or save it. Now, if we come to the blast furnace gas which is generated, we have already calculated 11 into 10 to the power 6 meter cube, and it is given that 1 meter cube of blast furnace gas generates about 20 gram of dust. So, the total dust would be 20 into 10 to the power minus 3 kg per meter cube, convert this. So, it will and convert it into tons. So, it will give you about 220 ton per day. So, that is a huge amount in a day you are generating the dust. You can imagine now that how much dust, if we take just a very minuscule amount, 20 gram, you are generating 220 gram just in the blast from that blast furnace, and you need a very elaborate dust cleaning facility for that. And this dust also you cannot just throw it, you have to and it has a value, quite a lot carbon and some mostly iron ore, and you cannot throw it, has a value. So, you have to use it, and that is where the agglomeration process comes into picture. So, we will come to the agglomeration. So, we had mentioned before in this course that about 50% or more fines are generated from mining to the blast furnace in transportation, crushing, grinding, beneficiation. So, all these lead to more than 50% fines generation, and they cannot be used directly to the blast furnace, as they would adversely affect the burden permeability in the blast furnace, and thus the furnace operation and its production. So, owing to the another also reason, the depleting reserves of traditional high grade iron ore, there has been considerable changes in iron ore resources available throughout the world. The proportion of fine material has increased considerably in iron ore. So, now we are really dealing more and more fines than the lumpy ore. So, we have to really switch to the agglomeration process, because these fines cannot be used directly. So, therefore, ore fines are agglomerated to make them suitable as ore feed to blast furnace, and there are two processes for this. One is sintering and another is pelletization. So, sintering is restricted in the size range of this. So, when size is less than or 10 millimeter or less, up to 2-3 millimeter, you can go for sintering. Pelletization actually it's in fact for very fine. So, usually the feed size is less than 300 micron, but majority of it 50% or more should be in this range, and you go for pelletization. So, we will come to the sintering. So, sintering of iron ore is a very complex process in which various phenomena take place, such as evaporation, condensation of moisture ahead of the flame front, calcination of limestone near the flame front, coke combustion in the flame front, melting solidification. Next slide shows a schematic diagram of sintering machine. And the main part of the machine are travelling grate, hearth layer, feeder, green mix feeder, combustion hood, sinter brake, suction boxes and devices, dust cleaners, sinter cooling and screening. So, this is a moving grate sintering machine. So, we feed the raw material. We will describe each of these separately, but I thought before we go to these separate things, it is necessary for you to understand the sintering process and sintering machine. So, then you can correlate what we are talking, if we talk about the raw material or if we talk about the sinter strand or any other or mixer or granulation, you can easily correlate this one with the actual sintering process. So, in this one you have a raw material bin where you have a ore fines, then you have coke, limestone, blue dust or some other material and water. You put it in a mixer, make the granules here. So, this fines comes in the granules of pellet form, which is more than 12 to 15, more than 12 millimeter in size. The idea is to have a narrow distribution, and these you feed it into the feeding bins, and which drops them onto a grate, moving grate. So, this is a moving grate which is continuously moving, and on this one the green pellet which has a moisture also, you put it there, but because sintering occurs at high temperature. So, the bottom layer is protected by some return sinter. You put it in this one, which is called the hearth layer. So, it protects overheating of the bottom layer or this moving grate. So, on that hearth layer you put the green mixture, and there is a leveler which leveled off the feed material, and so the bed height of this about 40 millimeter. It not 40 millimeter, it is about 40 centimeter. So, this is it varies from 30 to 45 centimeter in the range, and after leveling it off, it directly comes under the ignition hood. This is called ignition hood, where you supply the energy through the burners, which can be used for gas or oil or other things. So, this burner supply the heat, and which is around 1400 degrees Celsius or around 1300, and because this is top layer is subjected to this heat. So, coke which is inside in this pellet, it get burned and a flame front get established. So, once this pellet comes out under the ignition hood, already the flame front is established, and because the suction is applied from the bottom of this grate. So, due to the suction of this air this flame front travels towards down, and the downwards you are having all green pellets which has coke. So, it keeps on moving down, and the whole strand keeps on moving. So, once it comes out from the ignition hood, then it is exposed to the atmosphere, top one at the top, and the air is withdrawn or sucked through these wind boxes which are located at the bottom. So, as the air is sucked into this, the flame front moves downward, and the top layer gets sintered, and as you travel further, because it is exposed to the atmospheric pressure. So, top layer get cooled down, and by the time it comes to the last wind box, this whole product across the depth gets sintered here. And so, by the time it comes out at the end of this grate, everything is sintered, and it is broken into the pieces using sinter breaker. So, sinter breaker because this is like a cake which has to be broken into small pieces. So, the sinter breaker helps that to break it, and then you have a hot screen. So, where the very fine goes to the sinter return, the oversize comes again here, where you have a cooler and other thing to cool it down further, and again another screening. So, plus 15 millimeter size of sinters, you send it to the blast furnace, and minus 15 millimeter actually goes as a hearth layer to make, which we were talking about here, to make the hearth layer that actually goes there to make it. So, this is a moving grate and these wind boxes collect air. So, all combustible air and dust comes through this. So, you can get these also get collected. So, this is very fine returns, and this goes to the one of the bin here to use again for making the granules and pellets. And after dust catching the dust, gas goes out through the chimney. So, this is a brief description of this sintering machine, and we will be talking in detail about each of these process, how the mixing occurs, how the sintering is occurring, and how does it get affected by different parameters. So, this figure actually, in fact the right one is showing about the sintering machine, actual one. So, this is the ignition hood, you can see it, and this is once it is coming out from under the ignition hood, first layer is already very hot and get sintered, and you can see probably a bit this red hot underneath of the first layer, which means flame front has already established and traveling down as the gas is getting sucked from the bottom. So, the flame front is moving downward across the depth, and this sinter at the top is getting cooled by the cold air. And this is actually the other figure about the pelletization to make the green pellets or granulation, what we were talking. We will come to this. Also, this is you feed the iron ores and mixture and other things at one place, at other place you feed the water, and this is a disc pelletizer. So, it rotates, and this is a scraper. So, whatever material gets stuck is scrub that one, and with after some rotation and layering of the fines, you get granules of the size of 10 millimeter plus 12 millimeter, like that. So, this is a sort of a pelletization process. So, we will come to this a little later. So, there are various steps in the sintering. The first one is the raw material operation, as you have seen. The process starts from there. So, the raw material you have iron ore fines, coke breeze, flux, sinter returns, we have seen all those. Any other waste fines is there, we put that. So, there should be a strict size control for this. So, for iron ore it should be below 10 millimeter, usually between 3 to 10 millimeter. Coke breeze about 3 millimeter, and because it acts as a fuel, when the air is being sucked from the bottom. So, you know it is a self-sustaining flame front. So, that self-sustaining flame front comes from by mixing this coke into the pellet, and the size of this is also very important because that can affect the sintering process. Not just the sintering process, even the sinter which will get produced. Flux, that limestone, dolomite, limestone mostly calcium carbonate, dolomite is CaOMgO. So, it contains magnesium oxide also, and some other olivine and other flux one can use it, but mostly these are lime or magnesia based. So, again this should have also right size range, and you put it during this granulation, the flux, because in this one you are using not a very high quality coke or even sometimes coal you use it. So, you are really saving the coke in the blast furnace when you are using it in the granulation here. So, you are really saving the coke in the blast furnace, because for limestone and dolomite dissociation you need the energy. In the blast furnace it is supplied by coke, and here already it get dissociated by this low quality coke and other things. So, in that way you save coke in the blast furnace. Waste fines, these are the flux, dust, sludge, etc., from which it comes, and again it should have a size of 3 to 4 millimeter. So, because these are really fines mostly used for pelletization, but want to use for sintering, then you make a little micro nodules form of this and make sure it is in this range. Then sinter return, as we have seen, the below 10 millimeter goes to the bin as raw material. The next stage comes about the mixing and granulation. This is very important stage in the sintering. So, because that is where you are making the pellets of right size. So, all the materials are mixed properly before the start of granulation process. So, granulation or pelletization. So, water content should be between 4 to 9%, but usually about 8% or so, 7-8% they keep it. So, granulation is a complex process in which many input variables influence the product property, like particle shape, density, porosity, surface roughness, proportion of intermediate particles, surface area of the feed, mean feed particle size, and moisture holding capacity. There are others also. So, these are very important parameters in granulation. The idea of granulation, you have to get a narrow size range product, and it should be more than 12 millimeter, 10 to 12 millimeter and narrow range, because that will give the permeability to the bed. If you look at the let us say even this figure of this, when you are putting on these pellets over here and the suction is being applied from the bottom. So, bed should have a good permeability. If bed does not have a good permeability, your sintering will not occur in a proper way, and it will affect the productivity and efficiency. So, to make sure you have a optimum or good permeability of the bed here, it is very necessary that proper granulation should be done. So, and granulation process itself can be divided into two categories, wet granulation and dry. Usually in iron making we do not use dry granulation. Granulation again is a process where these fines you are making in the form of noodles or granules of the size of 10 millimeter or like that or more. But in the so these are used for even in chemical pharmaceutical sector quite a lot in drugs and tablet making. But here mostly we use in iron steel making the wet granulation. So, granulation is the act of agglomeration or process of crystallizing fine powders into grains or granules. So, size enlargement of fine moist particulate solids by granulation or walling is an important unit operation in sintering and pelletization. So, mostly the mechanism of wet granulation is snowballing, adhering the layer, collisions, abrasion, transfer. and you have the so many mechanisms are there where you have this droplet, winder droplet, it could be water, it could be molasses or anything, and then surface tension and capillary effects comes into picture, which finally together bonds into sort of a snowball type of structure in a finished agglomerate. And one of the mechanism also says that the product size or the granule size, the final granule size is directly proportional to the feed size what you are feeding it, and which can be given with this. So, where y is the granule size, the product, and z is the feed size, in case the proportionality constant, and that depends on the many parameter, moisture content of the feed and other things. So, there are various mechanism, but there is no sort of a I would say the determined mechanism or established one which one can use it confidently. So, still population valence is one of the one of the mechanism to describe the granulation process. Idea is to make the as narrow range as possible from this granulation process. So, the bed permeability can be improved and sintering can be done efficiently. So, the main aim of granulation is to eliminate fines by simple expedient of depositing and layering them onto coarse particle. The granulated product in turn is larger in size and narrower in size distribution than the original feed. The raw material like fine ore, return fines, coke bridge and limestone are stored in respective bins, as we had seen in the that figure, and are homogeneously mixed in a rotating drum with a small amount of water added to the mixture to get the green pellets. And there are various type of equipment which are available to do that. For sintering and the granulation, mostly we use this drum pelletizer or drum granulation. So, where the feed and the water put together and it keep on rotating with a certain RPM, and we get the product from the other end. Disc pelletizer we have seen in that photo also. So, this is a disc pelletizer where you feed the material at one end, water at another, and it rotate with a certain RPM, and the granules or pellet comes out. Similarly, you have cone, bowl, vibrating multi-cone sort of equipment to make the pellets, but these two are the main one which are used. This one mostly used in sintering, and this is quite this is used more in the pelletization when very fine ore is there. And the mechanism of it, if you look at in the starting, there is a nucleation of the, because the fines is there, very small fine material which act. So, some of these particles act as nuclei. So, nucleation mechanism is there, and once this nuclei are established, the layering of small particles, other fines then start happening with the help of what you are putting, water or molasses or any other something. So, that surface tension and capillary force come into picture, and it keep on layering with each rotation, and size keeps on increasing. So, in the starting it is a nucleation growth mechanism, then there is a transition period where these nuclei are not strong enough, sometimes they break, and sometimes they keep on growing. So, this is that transition period, and once this is over, then of course, the growth of the wall start happens. So, then all material keep on depositing fine on the big granules. and that increases the size of the granule. So, this is showing a bit idea how does it go, and this is showing where you put the feed and the water and a scraper which we saw this remove the whatever material got stuck at the bottom and make sure it follows the right direction these pellets. So, that is how the pelletization or granulation occurs. So, after once this mixing and raw material is over, as we have seen in that figure that it goes to the feeding. So, these granules or green balls are fed onto a moving strand which has thin layer of old sinter at the bottom to prevent the strand from overheating during the sintering process, and the bed height is regulated by leveling bar. So, this all is nothing much in that, and after that because the sinter strand is a moving one, moving sinter strand. So, it comes under the ignition hood and it is exposed to the burner flame and also suction from the bottom located wind box. So, eventually igniting the top layer of the sinter bed.